particle sizing minima. Based on the poster, we are able to choose two appropriate selective particle sizing method for each formulation, which is formulation A and formulation B. As for formulation A, it is a heat-sensitive protein powder which is fragile and the size range from 1 to 50 micrometer. So the first method you are able to choose is dynamic light scattering, or DLS. It is widely used in materials such as protein, and it is used in this fragile protein due to its non-destructive method. However, DLS is more sensitive in characterizing nanoparticle size, but it also can be measured in submicron particles. Some limitation can be observed when DLS cannot be used in high viscosity or turbidity and also very delicate samples. Based on its aggregation on polydispersed samples, DLS can manage aggregated samples. However, it cannot manage polydispersed samples as it cannot distinguish different particle size. The second method you are able to choose is laser diffraction. Laser diffraction has a wide dynamic range of characterizing, which is more sensitive in micrometer range. Laser diffraction also is a non-destructive method. However, some limitations can be observed when this method it is not suitable to be used in very diluted or concentrated samples. This method also must assume the particles used is spherical in shape. Based on aggregation and polydispersed samples, it can be observed that laser diffraction could not characterize aggregated samples because it will not reflect the internal structure. As for polydispersed samples, laser diffraction can be used to characterize it. The reason we are not choosing the other three methods is because sieve analysis and culture counter, the mechanism involved in these both methods will actually damage the fragile proteins. As for the microscopy method, it is not suitable to be used in a complex powder like this formulation A.
Laser diffraction. This technique measures particles from sub-micron to millimeter size, ideal for 50 until 500 micrometers. It is also rapid as it relies on light scattering principles like Meyer or Fraunhofer theory, which can analyze non-spherical particles effectively. It also has high reproducibility and precision as laser diffraction provides low relative standard deviation between runs. Plus, it provides volume-based size distribution, which is crucial for formulation performance. Now, sieve analysis. Best for coarse particles above 500 micrometers. This method is simple, inexpensive, and perfect for routine quality control. It works well for hard abrasive materials. Laser diffraction is highly sensitive, detecting even the particles in mixed samples, but it requires expensive equipment and trained users. It's non-destructive and fast. Sieve analysis, on the other hand, is less sensitive, especially for particles smaller than 45 microns. It still has limitations, which we need to handle it manually, time-consuming, and may be affected by mesh clogging. Plus, it is a destructive method. Laser diffraction is well suited for polydispersed samples, detecting a wide range of particle sizes simultaneously, but it's sensitive to aggregation, which can skew the distribution to appear larger. Sieve analysis, however, struggles with polydispersed samples and is easily affected by aggregation. Agglomerates can block sieves or be inaccurately retained. Dynamic light scattering is too sensitive for small particles only, which is not suitable for large and irregular particles like ceramic. Microscopy not practical for large sample populations and may miss overall distribution, while culture counter limited to conductive liquids, which is not suitable for ceramic powders.